Bad schema design is the tech debt you can never refactor away. You can rename a function, split a file, or rewrite a whole module on a quiet afternoon, and users never notice. But your database is different. Once real customer data is living in your tables, changing the shape of those tables means migrating every row, rewriting every query that touched them, and praying nothing breaks at 3 in the morning. The schema is the one decision that hardens like concrete. So let's get it right the first time. In the next 20 minutes we are going to design one real application together, from scratch, a simple online store with users, orders, and products. You will learn how to turn fuzzy ideas into entities and tables, how to connect them with primary keys and foreign keys, how one-to-many and many-to-many relationships actually work, the normal forms explained in plain English with a concrete before and after, when you should deliberately break those rules and denormalize, and finally the indexes that actually make queries fast. No hand-waving. By the end you will be able to look at any feature and design a schema you will not regret in a year. Start with entities. An entity is just a noun your application cares about, a real thing you need to store and look up. In our store the nouns are obvious, a user, a product, an order. Each distinct kind of thing becomes its own table. Users go in a users table, products in a products table, orders in an orders table. One entity, one table, resist the urge to cram unrelated things together. Now, every table needs a primary key. The primary key is a column, usually called ID, whose only job is to uniquely identify one row. No two rows share it, it is never empty, and it never changes. User ID 1 is Alice forever. That stable ID is the anchor everything else points at. And that pointing is done with a foreign key. A foreign key is a column in one table that holds the primary key value of a row in another table. It is a reference, a link. When an order belongs to Alice, the orders table does not copy Alice's name and email, it just stores her user ID, the number 1, in a column called user ID. That column is a foreign key referencing users.id. The database can then guarantee referential integrity. You cannot insert an order pointing at user ID 99 if no such user exists. Primary key identifies. Foreign key references. Get those two ideas solid, because every relationship you will ever design is built entirely out of them. Now let's connect the tables. This is relationship design, the heart of the whole thing. There are 3 shapes, and the trick every time is knowing which side holds the foreign key. First, one-to-many. One user has many orders, but each order belongs to exactly one user. The rule is simple and it never changes, the foreign key always goes on the many side. So user ID lives on the orders table, not the other way around. One row in users, many rows in orders pointing back to it. That is the most common relationship in any database. Second, many-to-many. An order can contain many products, and a single product can appear in many different orders. You cannot put a foreign key on either side to capture that. A column holds one value, not a list. So you create a third table in the middle, called a junction table, or a join table. We will call ours order items. Each row in order items holds 2 foreign keys, one pointing at an order, one pointing at a product, plus the extra facts that only make sense for that pairing, like quantity and the price paid. Every many-to-many relationship in the world is really 2 one-to-many relationships meeting at a junction table. Third, and rarest, one-to-one, one row here maps to exactly one row there. You mostly see it when you split a table for security or performance, like moving sensitive data into a separate profiles table. If you can draw these 3 shapes for your app, you have basically designed your schema. Now the normal forms, the rules that keep your data clean. People make these sound like abstract math, but they are just common sense with numbers attached, and there is a mnemonic that captures all of them, the key, the whole key, and nothing but the key. Let's start with first normal form. First normal form says every column holds a single, atomic value, no lists, no repeating groups crammed into one field. Here is a classic broken table. Someone built an orders table with a column called items, and stuffed a comma-separated list into it, pen times 2, mug times 1. It looks convenient. It is a disaster. How do you ask, how many mugs did we sell this month, when the mugs are buried inside a text string in 1,000 different rows? You cannot filter it, you cannot join on it, you cannot index it, you cannot even trust it. Nothing stops someone typing the product name 3 different ways. The fix is first normal form, break that list apart so each order line is its own row. 1 row per product in the order. That is exactly what our order items junction table gives us, order ID, product ID, quantity, 1 line at a time. Atomic values, 1 fact per cell, each row uniquely identified. The moment your data is in first normal form, the database can actually query it. Now second and third normal form, these only start to matter once a table has a composite key, a primary key made of more than 1 column. Our order items table is exactly that, its key is the pair, order ID plus product ID together. Second normal form says every non-key column must depend on the whole key, not just part of it. Watch what happens if we get lazy and pile extra columns into order items. Suppose we also store the customer name and the product name right there in each order line. The customer name depends only on the order ID, it has nothing to do with which product is on that line. And the product name depends only on the product ID, nothing to do with which order it is. Both of those depend on only part of the key. That is a partial dependency, and it violates second normal form. The symptom is ugly duplication. The product name, mug, gets repeated in every single order line that ever contained a mug, and if you rename it you have to update all of them. The fix, push each column to the table where its whole key lives, product name belongs in the products table key by product ID, customer name belongs in users. What legitimately stays in order items is quantity and unit price, because those genuinely depend on both the order and the product together. Now third normal form. Third normal form says non-key columns must depend on nothing but the key, no column may depend on another non-key column. The classic example, in a user's table you store both a zip code and a city. But city is determined by zip, city depends on zip, and zip is not the key. That is a transitive dependency. Store the same city under a zip and someone will eventually mistype one of them and they will disagree. The fix is to move that derivable data out. The key, the whole key, and nothing but the key, that one line is first, second, and third normal form. So normalize everything as hard as possible, right? No, and this is where good engineers separate from textbook engineers. Normalization has a real cost. Every time you split data across more tables, answering a question means joining those tables back together, and joins take work. On a read-heavy hot path, a product page hit 10,000 times a minute, a dashboard, an analytics report, those joins can become your bottleneck. So sometimes you deliberately break the rules and denormalize, you duplicate some data on purpose to make reads fast. A great example is an order total. Fully normalized, the total of an order is not stored anywhere, you compute it every time by joining order items and summing quantity times price. If your order history page is slow, you add a total column right on the orders table and keep it updated when the order changes. You are trading a little redundancy and some right-time bookkeeping for a much faster read. Another example lives in our own schema already. Order item stores the unit price at the time of purchase, even though products has a current price. That is intentional denormalization. The price on the product can change tomorrow, but the price the customer actually paid must never change. Here is the discipline. Normalize first, always, it is your correct, safe default that prevents update anomalies. Then denormalize surgically, only where you have measured a real red problem, and only when you have a clear plan to keep the duplicated copy in sync. Denormalization is not, normalization is bad. It is a targeted optimization you reach for second, with your eyes open to the right cost. Now indexes, the difference between a query that returns in 1 millisecond and one that scans your whole table. Without an index, finding all orders for user ID 42 means the database reads every single row and checks each one, a full table scan. An index fixes that. Under the hood it is a B-tree, a sorted structure that lets the database jump straight to the rows it wants instead of reading everything, the same way an index at the back of a book beats flipping through every page. So what should you index? 3 things. First, your primary keys, but you get those for free, the database automatically indexes every primary key. Second, your foreign keys, because you constantly join and filter on them, an index on orders.userid makes all of Alice's orders instant. Third, any column you frequently put in a where clause or an order by. But indexes are not free, and this is the part people forget. Every index you add has to be updated on every insert, update, and delete, so it slows your writes and eats storage. Do not index everything, index what your real queries actually use. 2 more ideas worth knowing. Composite indexes cover more than one column, and column order matters because of the leftmost prefix rule. An index on user ID then created at can serve a query filtering on user ID alone, or on user ID and created at together, but it cannot help a query that filters on created at by itself, because created at is not the leftmost column. Put the column you always filter on first. And a covering index is one that already contains every column a query needs, so the database answers straight from the index without ever touching the table, the fastest read there is. Index deliberately, match your indexes to your query patterns, and never just sprinkle them everywhere and hope. Let's put the whole store together in one picture. For tables. Users, ID as the primary key, plus email and name. Products, ID as the primary key, plus name and price in cents, and yes, store money as an integer number of cents, never as a floating point number, or rounding errors will haunt your accounting. Orders, ID as the primary key, a user ID foreign key pointing at users, a created at timestamp, and a status. That user ID foreign key is our one-to-many, one user, many orders. Then order items, the junction table that makes orders and products many-to-many, its key is the pair order ID plus product ID, it carries 2 foreign keys, and it stores quantity and the unit price paid. Every relationship in the app is visible right here, a user has many orders, an order has many order items, and each order item points at exactly one product. For indexes we lean on the rules we just learned, the primary keys are indexed automatically, and we add an index on orders.userid and on the foreign keys inside order items, because those are the columns every join and every lookup will hit. That is a clean, normalized, query-ready schema for a real store, and notice how a diagram this small can power a genuinely complex application. Good schema design is not about how much you add. It is about getting the shapes right. So here is the whole method, start to finish. 1. Find your entities, the nouns your app cares about, and give each one a table with a primary key. 2. Connect them with foreign keys, remembering the foreign key always sits on the many side, and every many-to-many needs a junction table in the middle. 3. Normalize, first normal form for atomic values with no comma lists, then the key, the whole key, and nothing but the key for second and third normal form, killing partial and transitive dependencies. 4. Denormalize on purpose, but only where a real read bottleneck justifies the right cost. 5. Index deliberately, your foreign keys and your filtered columns, and let the primary keys index themselves. Do those 5 things and you will design schemas you are proud of instead of ones you apologize for. I have written a full, free written guide to database normalization, and a companion guide on database indexing, both linked below, go read them, they go even deeper with more worked examples. And if you want the complete package, there is an optional SQL and database design pack in the description. Subscribe for more deep dives like this, and I will see you in the next one.